I really want to thank the VMSG committee for giving me this award. It's a real honour. VMSG has been a big part of my professional journey. I attended my first meeting when I was a master's student in 2017, thanks to the Liverpool organisers. Had a great time. And now I've moved to the US, I really realise how much I miss the small, friendly feel of a VMSG conference. So I'm very, very glad that I can attend this year virtually. So the talk I'm going to be giving today is about Thermobar, which is a new open source thermobarometry tool that I've developed during my postdoc at Oregon State. Many of the fundamental questions in Igneous Petrology require us to know, for example, how hot the magma chamber was. This might be important for looking at thermal rejuvenation or for getting accurate timescales from diffusion chronometry. We also often want to know how deep magma was stored. This is important for, say, interpreting geophysical signals of unrest during volcanic activity, and for answering bigger research questions like how does the continental crust evolve? What is the dynamics of magmatic systems? Where are they stored in the crust? We might want to know how wet the magma was. This can be important for looking at variations in eruption style in suites. So at the moment there's a wide variety of thermodynamic, empirical and machine learning based techniques to calculate these parameters from the composition of erupted melts and minerals. So for example, the exchange of jadeite between clinopyroxene and liquid, this reaction has a large change in volume and this means that it's sensitive to pressure. Similarly, various parts of amphibole composition, for example aluminum and amphibole, have been linked to pressure as well as temperature and the composition of the melt they grew from. And the exchange of anorthite between plagioclase and silicate melt is sensitive to both temperature and water content, so it can be used to determine these variables. So at the moment, almost all of these calculations are performed in Excel spreadsheets. And these are great, but there are limitations. Firstly, users must reorder their data many times. In each of these spreadsheets, so for example, this is at the top, the amphibole spreadsheet from Rodolphi, and at the bottom, the amphibole spreadsheet from Keith Paterka. You basically have to paste in your oxide data from the electron microprobe in the exact order that they do. And you can see, for example, these two spreadsheets put chromium in a different place. So you have to reorder your data when you're using different barometers to compare. These are also spread across a variety of environments. Most are in Excel, some are in MATLAB, some are in Python and some are in R. And in general, these MATLAB, R and Python scripts, these aren't really that user-friendly. They're not written with the aim that they can be used by people that don't know these languages. So you really have to be able to follow along the script to work out what it's doing and where your data outputs are being produced. And even if you're just using Keith's Excel spreadsheets, say you're looking at one volcanic system, but you want to look at lots of minerals, you would have a spreadsheet open for Cpx. You then probably have another one for OPX, maybe one for amphibole, maybe one for liquid, etc. So you just end up with an awful lot of Excel spreadsheets. The bigger problem with the available tools is that there's not really the advanced functionality that's required to answer many of the questions we have in Igneous Petrology. So for example, in a given volcanic system, you normally have a range of clinopyroxene compositions erupted. But in any specific eruptive episode, you normally only get one liquid composition at the surface. But we know those clinopyroxenes likely grew from a range of liquid compositions at depth. So what people have done is they have compiled liquids from many different eruptions at that volcano or even that volcanic region. And then they want to consider every possible liquid and clinopyroxene combination and work out which ones are in equilibrium. At the moment, if you wanted to do this in the available spreadsheets from Keith Paterka, you would first have to paste in all of your clinopyroxenes and then paste liquid 1 next to every single one of these and calculate whether they're in equilibrium, and if they are, go through and calculate pressure and temperature. You then have to do the same, line up all of liquid 2, all of liquid 3, etc. And using the standard number of liquid and Cpxs that are used for these tools, you'd end up with like 100,000 rows. It just can't be done in Excel. And there is an R script for this, but it is not publicly available and it takes quite a long time to run, like several minutes, whereas R equivalent code to do the same runs in seconds and is available. The second thing is often you want to iterate different calculations. So as I said, plagioclase liquid and anorthite exchange is sensitive to both the water content of the melt and the temperature. So at the moment, if you want to calculate temperature from plagioclase liquid pairs, you would probably download Keith Paterka's spreadsheet and you would enter your plag and your liquid compositions, but you would have to give it a water content and you might not know that. Similarly, if you want to calculate water using, say, the Waters and Lang expression, you can do as an Excel spreadsheet or a MATLAB code, you have to know temperature. And often people feed this hygrometer temperatures, say, from iron titanium oxides, but there's no guarantee that the plagioclase and the iron titanium oxide are recording the same temperature. Now what you could do is you could co-solve T and H, because the plagioclase equilibrium is dependent on both of those, and that's probably going to tell you the most things because you're doing it for the same mineral species. But unfortunately at the moment it would be very, very difficult to iterate those calculations because they're not in a single place. And this is really where Thermobar comes in. So it is open source and it is written in Python. This means that anyone can run it regardless of how much money their institution has, unlike MATLAB. And it also taps into the fact Python is a really rapidly growing language in the earth sciences. We've coded up more than 100 of the most popular thermobarometers, hygrometers and chemometers, involving all sort of the main igneous phases, and we're adding stuff for xenoliths at the moment. And this means that everything is finally in one place rather than in all these different spreadsheets. While the underlying source code is complex, and if you don't know Python, all 10,000 lines of it is probably a bit overwhelming, you never have to look at this. It has been packaged up into nice, easy functions which even non-coders can use. So for example, this is the code for calculating amphibole-only pressures, or a segment of it. But all you have to do is type calculate amp-only pressure, tell the function what amphibole compositions you want to use, which you've loaded in, and tell it what equation you want to use. So in this case, you're saying you'd like to calculate pressures using Ewan Much's 2016 expression. And it is very simple to download locally. Once you have Python installed on your computer, which is easy nowadays through Anaconda, all you have to do is type pip install Thermobar and it will download everything you need off the internet and it's all ready to go. There's no other steps for you to do. The final thing is, unlike all of the spreadsheets, Thermobar doesn't care what order your data is in. All you need to do is give it your oxide content. So for example here we're feeding in the liquid composition and we tell Thermobar this by putting _liquid. These can be in any order, so whatever order the data comes off your probe, you can just quickly add _liquid if it's a glass and you're ready to go. And say you want to calculate plage-liquid pairs, you just have a second set of columns for your plagioclase compositions, again with this _plage, order doesn't matter. And you can also add in other columns, you can have a latitude column, the pressure say from a melt inclusion column, and this really would quickly allow you to plot the calculated pressure and temperature from thermobarometry against these other variables. I'm not going to go through worked examples because I understand everyone at VMSG probably isn't going to want to do thermobarometry at some point in their life, so I'm going to direct you towards this read the docs page I've developed online. And you can see on the left hand side there's a contents page. And if you go down here, the first thing you probably want to do is watch the narrated YouTube videos. There are a series of these and I suggest an order to watch them in. So first off, it'll just introduce Thermobar, how to download it. If you haven't used Python before, it'll quickly introduce how to run cells, how to load in data, etc. And then what you'll find is that there's a series of videos for specific applications. So say you want to do Clinopyroxene liquid melt matching. You could watch this video and you can download the Python notebook and the Excel workbook and follow along as I perform the calculations. And we show various things you might want to do, like change the filtering criteria, as well as different ways to visualise the data you've calculated in pressure, temperature, space. Some other functionality, as well as doing thermobarometry, it also makes a series of plots you might want when investigating mineral compositions generally. So you can easily make an olivine liquid equilibrium diagram with various options for the olivine KD. You can plot pyroxene compositions on a ternary diagram. You can plot feldspar compositions on a ternary diagram, and there's many more features which you'll all find described in that read the docs page. So this is kind of the end of part one of the talk, and I just really want to emphasise this tool is designed for people with no programming experience. You don't need to be able to use Python. All you need to be able to do is click download buttons, watch YouTube videos, and you will be able to follow along. And on the plus side, you will actually learn Python in the meantime, and that means you can use it for a wide variety of things. And I think once you start with Python, it's going to be hard to go back to Excel. At least that's what I found. And we always welcome user feedback, requests for new functions. If there's something clever you've seen in a paper, people are doing Excel or proprietary code that they're not releasing, let me know and I'll try and make an open source version of it. So the second part of my talk is what I'm actually being paid to do by my bosses rather than what I've actually done for my postdoc. And anyone who follows me on social media might just think I've spent the last year climbing various Cascade volcanoes, and while that would be reasonably accurate, the aim of my project overall is to look at magma storage variations in the Cascades. So for example, as we go from south to north along the arc, are there variations in storage depth? Do these perhaps correlate with the crustal extension state, the flux of magma coming in, the fluid flux coming in, or any other variables that we can kind of work out? And while a variety of methods exist to get magma storage depth, in the Cascades it became pretty clear that what we were going to have to be using is Clinopyroxene. The Cascades is a relatively dry arc, there isn't amphibole in every place, and as many of you know, amphibole barometry has problems as well. So, as I said briefly, Clinopyroxene barometry works from the fact that this exchange of this jadeite component has a large volume change and is therefore a pressure sensitive reaction. And jadeite is calculated effectively from either the sodium or the aluminum content of the Clinopyroxene. In most cases, it ends up being the sodium content. And a wide variety of expressions exist for calculating pressures from both Clinopyroxene liquid pairs and just Clinopyroxenes, and some of these studies are listed here. But while people like David Neve have done a really good job of working out what barometers are best in Iceland, and various people like Masota have done the same for Etna, there really hasn't been a comprehensive look at what thermobarometers behave best in arc magmas. And you can see this in this compilation I've made, so these are studies since 2012, and people are using a wide variety of different combinations of equations. In fact, in the literature I found 16 combinations of barometers and thermometers. And the reason there are so many options is not only do you have all the different barometers, but all of those Clinopyroxene barometers have a temperature term pretty much. And that means that as well as picking a barometer, you also have to pick a thermometer to calculate temperature, to then iterate your barometer with. So we really want to work out which of these 16 behaves best so that I can apply them to the Cascades. One of the ways that people are currently picking is using the stated standard errors on these barometers. So for example, for the Peterka et al. 2003 barometer, they have this plot in the paper which shows the calibration data, and they show that this model fits this calibration data with a standard error of 1.7 kilobar. But this is the fit to the calibration data. If you overtune a model enough, you could perfectly fit your calibration data. This is not an assessment of how this model is going to behave on data it hasn't seen before. Similarly, a lot of studies quote 1.3 to 1.4 kilobars of error for the Neve and Peterka barometer. Again, this comes from this figure in the paper, which is the data used to calibrate the model. If we want to assess a regression, what we need is data that was never used at any point during the calibration routine, to then feed that data into the barometer and to check how good a job it's doing. But the problem is, while these barometers use a relatively small number of data, 77 experiments here and 113, many of the thermobarometers of Keith Peterka use the entire LEPA data set, and this was a big compilation of about 1,000 Cpx liquid experiments put together in 2008. So we have at the moment no way to assess those barometers because all of the compiled data has been used to calibrate them. So what I did is I looked through the literature and I found all the sort of experiments relevant to arcs and sort of relatively hydrous magmas conducted since 2008 to give us a new test data set to assess these various equations and which ones are doing a good job. And you can see all the studies I compiled here. This is about 600 Cpx liquid pairs. So then what I did is I used Thermobar. I took the Cpx and the coexisting liquid compositions from these experiments, and I asked Thermobar to calculate the Cpx liquid pressures using all combinations of equations. And then what I've done is I've plotted an XY graph where the x-axis is the experimental pressure and the y-axis is the pressure that we calculate. So for example, on this plot, this is the pressure we calculate by iterating Peterka 2008 equation 33 with the Neve and Peterka 2017 barometer. And similarly, this is iterating equation 33 and equation 30 from Peterka 2008. The statistics for these fits are shown down here, and the one-to-one line is shown in red. So if these barometers are behaving perfectly, every dot would lie on the one-to-one line. And you can see this is very much not the case. So for example, the Neve and Peterka barometer iterated here, this has an R-squared of only 0.27, and it's got a gradient of 0.54, whereas that gradient should be 1. Similarly over here, this combination has a higher R-squared value, so 0.47. But what you can see is it really is overestimating these low pressure experiments. This means, say you feed it a Cpx composition that formed at a kilobar, it could return you a pressure of up to 8 kilobars, and that's really problematic. So then the question became, why are these barometers behaving so badly? And there are three kind of big sources of error that we need to think about. The first is analytical error, because we have to measure these experiments to get their compositions, which we're then feeding into these thermobarometers to test them. And imprecision on the electron microprobe is basically controlled by your peak to background ratio. So the more counts you have in your peak relative to your background, the more precise the measurement of that element is. There then are there various problems. So for example, different labs use different primary standards, and there is variability within these chips of natural materials. So this means, well, the tephra community has shown nicely that different EPMA labs produce different results. So similarly, different labs measuring clinopyroxenes are going to get slightly different compositions. And if a variety of labs is used to calibrate these barometers and to test them, that can introduce a fair amount of noise. And then there are problems with beam migration. So we're looking at predominantly hydrous glasses here. We know if you count for too long, you're going to be losing sodium from that glass, and that's going to affect your pressure calculations. Then there are various other things that could introduce error, like instrument drift or sample preparation. There are then experimental sources of error. A main one is that many experimental products are zoned, sometimes sector zoned for clinopyroxene. So if you only measure one zone of the clinopyroxene and not very many of them, you can get a completely different composition from, say, if you had measured this zone instead. And then there are problems, for example, several experiments, quite a lot of them actually, for clinopyroxene liquid, did not put chromium into their starting materials. Yet it has been shown that Cpx liquid equilibrium, and particularly the appearance of Cpx on the liquidus, is dependent on the chromium content. So by some experiments having chromium and some not, that can introduce a fair amount of scatter into your calibration. And then the third source of error is model fitting. So if you imagine the leopard data set is shown in blue, like cyan colours here, you can see you could fit a model to the calibration data that does quite a good job. But if you extrapolate this up to higher X values, it's going to do a very bad job of fitting your new data, which may lay slightly outside the calibration range. There are also problems associated with, say, model overfitting, particularly for machine learning techniques. So for the rest of this talk, I'm going to specifically focus on analytical imprecision, because this is the most important, it seems, based on the analysis I've done. When we run the electron microprobe to measure clinopyroxene compositions, what we normally do is measure primary standards, and then repeatedly throughout the run, we measure secondary standards or known reference materials. And for clinopyroxene, this is typically the Kakanui augite. So say we measure 20 of these throughout the run, we then calculate the standard deviation of each element, convert it into a percent, and this basically gives us an indication of the precision or the imprecision of our measurements. This typically comes out between 5 or 10%, and then what we do is in the paper we say that the precision and accuracy of measurements was between 5 and 10% based on analysis of these reference materials. But the problem is the imprecision of electron microprobe analyses is very closely related to the concentration of the element. Higher the concentration, the more X-rays that are generated, the more counts we get, and the more precise our measurements are. And we can model this using the count rates on primary standards. So if we look at one of these models, while the precision for high concentration, such as in this augite standard, is about 5 to 10%, it rapidly ramps up to higher values as the sodium content drops. And we can overlay on this model line measurements made at the MIT probe lab for the experiments of Mike Krasinski et al. 2012. And these are basically the precision that was calculated by the probe and outputted in the software, and this is based on the count rates. And what you can see is they are way higher than our secondary standards, kind of worryingly high, more than 15%, up to 40%. Now, in any given experiment, you should be measuring multiple clinopyroxenes. And if you calculate the variability in elements in those measurements, if they lie on this line, then that means that the variability of sodium in a given experiment is largely controlled by analytical imprecision. If they lie well above this line, in addition to this source of imprecision from counting, you also have additional true variability. So this might be zoning, for example. So if we look at the actual experiments measured on this probe, which are these yellow squares, you can see they pretty much lie on this line, considering actually a variety of probe sessions we use with slightly different conditions. So this indicates that sodium variability, which let's remember controls jadeite, which controls pressure, is largely controlled by the way we're using our microprobe. We can look at the same thing for the experiments of David Neve. Again, these are the software outputted values shown as circles, and the experimental variability is shown as these squares. And again, sodium variability is being controlled by how long we're counting for on the probe. The opposite is true for aluminum. Because the contents are much higher in Cpx, you can see the theoretical model value and the software outputted measurements are very, very low, errors much less than 5%. The experiments show a lot more variability. And this indicates that they are truly zoned, and based on correlations between different elements, this is actually sector zoning, and this is very common in experiments. So what we want to know is the variability in pressures that we calculate, which basically is the reason we have so much scatter for these barometers. Is it being controlled by analytical variability, or is it being controlled by experimental variability? So how we do this is, for David Neve's experiments, we have basically taken those outputted sigma values from the probe, so the error we would expect just based on counting statistics for each element. So say element X, we know its mean value from the measured value in the experiment, we know its sigma based on counting statistics from the probe, so we can simulate a normal distribution of what that element would look like purely because of analytical imprecision. And we do this for every element, and we basically generate 10,000 Cpxs that have major element contents following this distribution. We then feed these synthetic Cpxs into various barometry equations. So for example, here, this is a Cpx liquid thermobarometry combination. And we're not including any error on the glass here, this is just the error on the Cpx. What you can see is, based on the contouring, more of the simulations lie at these pressures and less lie at these pressures. And we can contour this, so 67% of our simulations are surrounded by this purple line, and 95% of the simulations are surrounded by this black line. And what you can see is, based on measuring a single homogeneous Cpx, just your analytical error can generate pressures ranging from about 5.5 kilobars all the way down to -2 kilobars. What we can then do is we can overlay the compositions of Cpxs actually measured in the experiment in these pressure temperature spaces. So each Cpx from a single experiment is shown as a dot on here, and you can see this fits almost perfectly within the Monte Carlo simulation. If there were an additional source of scatter resulting from, say, sector zoning, these dots would extend much beyond the simulation, but they don't. So really, the spread of pressures and temperatures in Cpxs from a single experiment is controlled by analytical variability. This is Cpx only on the left-hand side. On the right-hand side, this is Cpx liquid, and you can see the same thing. And in fact, the spread of pressures is even bigger for Cpx liquid. Now, many of you are probably thinking, well, this error is random analytically, so if we measure enough Cpxs from a given experimental charge, it's going to average out. And that's true if you measure as many Cpxs as David did. Unfortunately, when we compile the number of Cpxs measured in different experimental charges, we see 40 measured a single Cpx, and 43% of the entire dataset measured less than 5 Cpxs. And you can see what this would do looking at the simulation. If your first measurement happened to lie in the centre, say, for that 1 Cpx, you might well lie on the one-to-one line. But if your single Cpx analysis lay at the tail of this distribution, you could easily lie 3 kilobars off this line, even if the barometer is actually perfect, just based on the analytical uncertainty. So this can account for a lot of the scatter we see about these one-to-one lines when we look at these global data sets. This is also a problem not just for experiments, but for natural Cpxs. Even if your Cpx and liquid compositions grow at a single pressure and temperature and have a fixed composition, the noise introduced by commonly used analytical conditions for Cpx means that you could end up with a span of pressures and temperatures spanning 4, 5 or even 6 kilobars. And because of the correlated array of this pressure-temperature space, these have often been invoked as transcrustal magma storage when it is just analytical error. So in conclusion, unfortunately, based on the available experimental data, we can always expect 2 to 4 kilobars of scatter. We likely need to reanalyze a lot of existing experiments to improve the precision on sodium. We can do that using more counts. We need either longer count times on sodium or higher beam currents. We've done tests at OSU, even 100 nanoamps in several minutes, sodium isn't migrating in Cpxs, so that doesn't need to be a concern. We need to make sure we're not assessing precision using secondary standards on elements where the secondary standards have different concentrations. We need to make sure we're propagating our errors in natural systems and making sure if we really think there's transcrustal storage, we can show that the distribution of pressures is much wider than we expect from analytical error, rather than just using the published 1 sigma values on the barometers, which aren't really that useful because that's mostly the calibration data set. And we need to make sure we're doing better data reporting, not just of how we collect the data, but also what equations we're using and exactly what matches we're using, so that when better barometers do come along, the data can be reanalysed and we can get a better understanding of magma storage in the crust.